Proper protection starts with the selection of current transformers. The following is a simple procedure that can be used to check whether or not there is the possibility of CT saturation. This procedure is as follows. The first step is to ensure that the primary rating of the current transformers is equal to or greater than the expected full load current. We can determine the primary rating of a CT by looking at its ratio. For a ratio of 100 to 5, a CT has a primary rating of 100, meaning that no more than 100 amps should be passed through the CT under normal operating conditions. The second step is to ensure that the CT can drive what is called the attached burden at the worst-case fault current levels without saturating. The burden refers to the total load resistance of the secondary circuit. The calculation for the burden is CT secondary resistance, which is the amount of resistance on the secondary windings on the CT, added to the connection wire resistance, which is supplied by the manufacturer, added to the relay's burden resistance, which is the resistance within the protection relay. As explained in the previous section, a CT becomes saturated when the voltage secondaries reach the knee point of the excitation curve. To determine whether the CT can drive the attached burden under worst-case fault conditions without saturating, we must determine what the CT's secondary voltage will be at the time of this fault. The CT secondary voltage at the time of fault is equal to the burden resistance times the maximum fault current divided by the CT conversion ratio. The resulting value is then plotted onto the CT excitation curve. If the value plotted on the curve is below the knee point, then the CT will not saturate under these worst-case fault conditions. If the value is equal to or greater than the knee point, then the CT will saturate. Now we will look at a practical example to help us further explain this calculation. Let's assume that we have a motor that draws a maximum full load current of 285 amps. The first step is to choose the appropriate CT. It is customary to select a CT that has a primary rating falling between 50 to 100% of our maximum full load current, in this case 285 amps. Possible CTs for this use would be 300 to 5, 400 to 5, and 500 to 5 CTs, because the primary rating falls between 50 to 100%. In this case, we would select the CT that would fall the closest to 100%. The reason for this is the higher the CT ratio is over the full load current, the less sensitive that CT will be. Since accuracy is always imperative, we will select a CT with a 300 to 5 amp conversion, where the primary rating is 300 and closest to the 100% primary rating. The next step is to ensure this CT doesn't saturate under worst-case fault conditions. If it does, a higher ratio CT, such as the 400 to 5 CT, may need to be chosen. The first step in determining whether a CT will saturate is calculating the maximum current that will appear on the primary of the CT under a worst-case fault condition. The maximum fault current at the load is determined by a fault study, and in this case was determined to be 6,000 amps. Next, we will calculate the secondary resistance, or burden, using the stats provided. The phase CT's secondary resistance, that is, the resistance of the windings on the CT, is equal to 0.088 ohms. The length of each wire from the CT to the relay is 50 meters and has a rated resistance of 2.5 ohms per kilometer. The total burden is equal to the CT secondary resistance, which is 0.088, plus 2 times the lead length of 50 meters multiplied by the lead resistance of 2.5 ohms per kilometer, and then divided by 1,000 meters. This is then added to the relay burden of 0.008 ohms, resulting in a total burden of 0.346 ohms. Now the secondary voltage at the time of a worst-case fault can be calculated. First, the total burden resistance, 0.346 ohms, is multiplied by the maximum fault current, 6,000 amps. The result is then divided by the CT ratio, 300 to 5, concluding that the secondary voltage at the time of a worst-case fault is 34.6 volts. With the maximum secondary CT fault voltage calculated, the final step is to refer to the CT excitation curve. By plotting the 34.6 volts value on the excitation curve, we notice that it falls well below the knee point, indicating that it will not saturate under a worst-case fault condition. If the factors affecting the burden were ever to change, or a higher fault current is measured, These calculations must be repeated to ensure the CT does not saturate.